All right, so today we are going to expand on our look at springs and spring energy. Last time we spent a long time looking at the uh, looking at the energy of a horizontal spring. Today we are going to look at the energy of a vertical spring, and we'll see um, what interesting results we get from just adding that little wrinkle. So we have a vertical spring, and for the purpose of this of our starting discussion, we are going to assume that the spring itself has mass that is negligible, and all of the mass is in this block that we're going to hang on the end of it. We're going to assume that we have a block with a block in spring that it hangs at some preferred length, and we will there's some stretch due to the hanging of the mass on the spring. We'll call this maybe delta x0. So this is the stretch of the spring that's just due to the static hanging of the weight. And then we're going to mess with it. We're going to pull it down a distance a, and we're going to watch it oscillate. Right, so it'll also come up some distance. And we have a few questions, like what is the velocity at any given point? Does what is this maximum compression that the spring gets? Like what is this distance here? And is A the same as B? And can we write a function for the position of the mass as a function of time like we could for the horizontal spring? So just for reference, the horizontal spring looks something like this. With omega equal to the square root of k over m, right? And this was, for horizontal springs. So what's the wrinkle here? Like what's different about a vertical spring versus a horizontal spring? Anybody chime up? What's the wrinkle here? Nobody? Oh, come on. Somebody's got to have an idea. Uh, Train master. Oh, Zachary. Yep. Gravity. Gravity is the wrinkle here. So when we were looking at the horizontal spring, we only had to deal with the kinetic energy of the mass and the stored potential energy of the spring. But now we also have to deal with the gravitational potential energy of the system as well. And that could be an issue. So let's write down what the energy is at different points. So just like before, we will call the maximum stretch point A, we'll call the minimum stretch point B, and we will call the equilibrium length here C. So just like in the horizontal case, so we have no external forces. Right? So this implies that there's no change in energy of the system. And here, of course, we're not including, for the moment, we're not including things like air resistance, right, internal friction of the spring, um, things like that. We can develop the tools to deal with those later, but for now, we're just trying to simplify it, right? So we're not losing energy due to friction because we haven't really talked about how to deal with heat energy yet, which is where friction takes energy. So in 182, you'll start talking about heat, and you'll start to develop an understanding of how we could keep track of that energy as well. But for today, just looking at mechanical motion, so no external mechanical forces, no change in energy. So we can write down the energy at any of these 3 points, uh, and say that the quantity of energy is the same. For simplicity, we need to define a point where the height is 0. Right? And this is something that we have to do anytime we're dealing with gravitational potential energy. So if we have, right, gravitational potential energy equals mgh, right, we need a point from which h is measured. So there has to be a point where this energy is 0 in order for the height to make sense. So there's 3 different logical choices here. We could choose A, B, or C to have 0 height. But I'm going to choose A for this initial discussion. So this is the point at which height is 0. So now let's write down what the energy is at these different points. At A, we're at maximum stretch, which means that we've got no kinetic energy, right? We have the mass has stopped, it's going to turn around, and it's going to swing upward the other way. So no kinetic energy means we only have potential energies. And in fact, we've defined the height at point A to be 0, so that's got no gravitational potential energy. It has only spring potential energy. And the amount of stretch is however much stretch we have at C plus the amplitude of this oscillation, the downward amplitude. At B, again, we're at the maximum height. So we still have no kinetic energy because it's about to turn around and start coming back down. So the speed has been zeroed out. So we only have spring potential energy and gravitational potential energy. And then the energy at C, we're going to have all 3 kinds of energy at C. All right. Any questions about this setup so far? So does it matter whether at point B whether we are just have whether it's actually undergoing compression or whether it's just the least stretch? Right? And I guess another way of asking that is, does it matter if B is bigger than x sub 0, delta x sub 0? Okay, so we've got an intuition that it does matter. Can you expand on that?
Um, if B has to, or my intuition is basically B would have to be bigger than C or X sub 0 because the system wouldn't be moving if like B was just went back to 0, or at least it would only move in like one way, then stop immediately at 0 for some reason. So that doesn't make much sense.
Okay. So that's a I mean that's an interesting point. So like that begs the question, like what does happen if we've got this oscillating mass and we cross the point like where the spring would like happily like the length of the spring would be if there was no mass on it. So if the right, because if we don't hang a mass on it, we assume that like there's it's going to be at a shorter length, right? And in fact, this distance between the unweighted spring and the length it is when we hang a mass on it, that's what we're calling delta x zero. So I guess there's two cases. Let's be thorough here. But Matthew, you had correctly identified the piece of interest here. So if B is smaller than delta x zero, no problem. The spring is actually under tension the whole time, um, and we don't have to worry about it. If what if B is bigger than delta x zero? That means that this factor here, this x0 minus b, is going to be less than 0, right? It's going to be a negative number. And what does that indicate, right? If when we've got Hooke's law, right, that the force exerted by a spring is equal to negative k delta x. What does it mean if delta x is negative? Right? We've been talking about Hooke's law for a couple of classes now. So yeah, what does it mean if we have a negative value for delta x? Josue, any idea? Prada or Sorka?
Being like a positive number.
Yeah. What are so we've got Hooke's law, which is force exerted by a spring is equal to negative k delta x. So what's the are we allowed to have both positive and negative numbers for delta x? And what does it mean if delta x is positive or negative? Keys, that's exactly right. Um, if delta x is negative, the spring is being compressed. And if delta x is positive, the spring is being extended. Uh, so that is exactly right. And we're allowed to do both with the spring. We're allowed to stretch them and we're allowed to compress them. So if delta x naught is less than b, it means that this factor is going to be negative. That just means instead of stretching the spring, we've gone from stretching to compressing. Right? And if the spring is compressed, well, it stores energy in the same way, right? And we're going to square it down here so that the negative number becomes a positive number anyway. So do our expressions for energy down that we've written down for A, B, and C, do they change if the spring is in compression versus if it's in tension? Like, do they care about the sign of the of delta x, basically? Yeah. So we're going to square it. So the energy goes as delta x squared. Um, so compression or tension, right? Uh, they can both store energy. So um, that is not necessarily intuitive. So I wanted to be explicit about it. Let's copy this little left-hand bit to a new slide to give ourselves some room to work on this. Okay. So which two positions shall we compare first? Let's compare position A and B. So the energy at A has got to equal the energy at B. Um, so we should have 1/2 K. I'm kind of regretting not calling delta x naught C at this point, but I feel like it's too late to go back. Okay, so in this expression, our only unknown is really b, right? Um, right, x naught, right? We could have kind of observed at setup when we added a mass to the spring, so we could have observed that. The a, we chose how far to kind of pull the spring down when we started this oscillation. So the rest is known. So let's see if we can get an expression for b in terms of everything else. First, let's expand this binomial here, since we've got a b inside. So we have 1/2 k delta x0 squared minus k delta x0b plus 1/2 kb squared. And then plus mga plus mgb. Prada, would b be the same as a since a is pulling the spring forward while b is pulling it back? Maybe. That is what we are here to find out. So that, I mean, that's a good intuition to have about the problem. If the spring was horizontal, a would absolutely be the same as b. But what we are trying to figure out is if the addition of like of gravity here upsets that symmetry. This term on the left here, by the way, I'm just going to call this, right? I'm just going to call this E, right? Since that actually represents the total amount of energy in our system. Do we want to? Actually, no, let's not do that yet. I changed my mind. Let's expand that binomial. We have 1/2 k delta x0 squared plus k delta x0 times a plus 1/2 k a squared. Alright, so we have a 1/2 k delta x0 squared on both sides of the equation. So we can just go ahead and cancel that. And then I'm going to move everything to the right-hand side of the equation. So we have 0 equals 1/2 kb squared plus b times, I'm going to factor out a b from all the terms that have just b to the first power in them, these two terms here. So we have mg minus k delta x. And then we have all the terms that don't have b in it. So plus mga minus 1/2 ka squared minus k delta x a. So maybe, in fact, I'll also factor out an a to the first powers. So we have the quadratic term. Okay. Is everyone with me here? So here is where we're going to validate Prada's intuition. If so, we're going to we assume at this point we know that we could solve for b as a function of a. If nothing else, we could use the quadratic equation. But let's look at the terms that are that are quadratic in a and quadratic in b. Right. So we have 1/2 kb squared minus 1/2 ka squared, and then the terms in other way around. And then we have the linear terms. Can we, like, is a equals b a solution to this equation? Anyone? So Raul says maybe. Actually, if we just plug in a equals b, we definitely get a cancellation in the first term, right? The quadratic term goes away. But in the second term, the linear term, we have an a plus b. So we end up getting 2b equals, or sorry, 2b times mg minus k delta x. So if a equals b, right, then we get 0 equals 2a times So if this is what we get left, is this a valid equation? Is 0 equals 2a times mg minus k delta x0? Right? We have 0 on one side. We have other stuff on the right-hand side. Is this stuff on the right-hand side 0? Jaden, you say yes without the question mark. Can you explain? That's all right. So, but Jaden's right. It is 0 because this thing in the parentheses is 0. Right? Why is this 0? Well, let's take a look at what the spring was like before we started making it bob up and down. We had the spring force pulling the mass up, we had its weight pulling it down, and we defined C, like point C, as the height that the mass rested at, just under its own weight. So here we had, using Newton's second law, sum of forces in the y direction is 0 because it's not moving, equals mg minus, or equals k delta x minus mg. So yeah, k delta x naught and mg are forces that are the same size based on how we defined the problem to begin with. So bam, there we go. So yes, A is equal to B. Check. Whew. Good job, Jaden. So that was the first question that we wanted to answer about the vertical spring. Is do we have the equal positive and negative amplitudes? And we do. Let's take a look back at our setup here. Another question that we would like to answer is what is the velocity of the moving spring, like as a function of height, right? And how does that compare to our expression for the velocity of the horizontally moving spring? And maybe also, what is the maximum speed? Right? We can answer that question too. Whoops. Let's start with what is the maximum speed? And the maximum speed, well, before we even have that, let's actually analyze what is the speed at the middle, right at point C. Because we suspect that that's where the maximum speed will occur. Or at least that's where it would have occurred in the horizontal motion. So energy at A equals energy at C. We have 1/2 k delta x naught plus A equals 1/2 k delta x naught squared plus mga plus 1/2 mv squared. So again, let's expand out the binomial on the right. Get 1/2 k delta x0 squared plus 1/2 ka squared plus k delta x0a. And then everything on the right-hand side comes down for the moment. And very nicely, we get the 1/2 k delta x naughts on both sides, so we're going to cancel those out. And the thing that we're interested in here is v. So everything with a v gets to stay on the right-hand side. Everything without a v has to go to the left-hand side of the equation. So we get 1/2 ka squared plus k delta x0a minus mga equals 1/2 mv squared. Let's solve for v. So we're going to multiply everything by 2, divide everything by m. So for this first term, we'll get rid of the half, and then we'll have k divided by m. And last time on Monday, we found that it was actually convenient to replace k divided by m with omega. So let's try that same, or omega squared rather. So let's try that same trick here. So here we have omega squared a squared plus 2 omega squared delta x 0a minus ga, or 2ga rather. Square root of this whole thing, that should give us v. Now, for reference, for the horizontal case, this is not the expression we had, right? So in the horizontal spring, we had, right, v at c equals omega a. So is this expression that we have for v here, is this bigger than, less than, or equal to our expression for vc in the horizontal case? Think on that for a moment. Tell me what you think. Okay, so on the count of 3, I want everyone to type an answer in the chat. We're all going to do this at once. Ready? So I'll type then. You put either a greater than sign, a less than sign, or an equal sign. We're going to see what everyone's intuition says. Ready? 1, 2, 3. less than Cortez, cute. Both less than and equal than, or less than and greater than. So, our winner of today's prize, which is completely fake internet points, is Addison Sorka. So, in the last slide, right, we found that mg equals k delta x, right? On this slide, we have k delta x times a minus mg times a, right? Well, if k delta x minus mg is 0, multiplying that by a, you still get 0. So these two terms, they cancel out. And in fact, we do have exactly the same thing as we did in the horizontal case. All right, questions, comments? Maybe why did we bother working on this if it turns out to be exactly the same as the as the horizontal case? So I guess let me pose that question to you all. Why did we spend half an hour working on this if it turned out to be exactly the same as the horizontal case? That's exactly right, Jaden. There's questions for both. They're not the same questions, and until we worked it, it wasn't at all obvious that adding gravity would have no effect on the motion of the spring. Right? Like that's completely unintuitive. Now, there are definitely um, uh, some unanswered questions that we can talk about here. There's, in fact, this is going to be our last day talking about springs. I could frankly spend the whole semester talking about springs, harmonic motion, elasticity. Um, this is frankly like amazing stuff. But we just don't have the time to do an entire class just on springs, unfortunately. One thing that I do want to do a couple of things quickly. Um, one is to ask, well, is it reasonable to assume that a spring has no mass, like we did in this problem? So when we started our derivation, we made the assumption that we could completely neglect the energy of the spring. So is that reasonable? Maybe it's reasonable. Um, let's actually do a quick calculation. So, other than springs, something that I also like a lot is Wikipedia. And I know not a lot of instructors will say that, but frankly, when we're talking about math and science, who's going to bother editing math and science wiki pages except for turbo nerds? Um, and like this is actually where the wiki model shines because there is nothing that a turbo nerd loves more than correcting another nerd. So if a math or science page is inaccurate, it will make a nerd's day to be able to correct it. So there is a way of calculating how much of a spring's mass should be included theoretically. And actually, you all should remember this because this is a post-lab question for a lab that you haven't done yet. So let's look at a spring and let's not assume that the spring has no mass. Okay. So what we want to do is actually we're not going to hang a mass on it on the end of it at all. Like it's just going to hang under its own weight, and then we're going to disturb it and oscillate it the same way that we did with the mass on it. So what if we had if there was no mass on the end of the spring, but instead the entire spring had a mass, right? And the idea here is that we try to calculate the entire kinetic energy of the whole spring, and we're going to do it with an integral. So we're going to say the kinetic energy of the spring is if we integrate over all of the little bits of mass. When I say little bits of mass, I mean we take infinitesimal slices, like so. And there is an amount of mass dm in a thickness of the spring, which is dy thick. Then the kinetic energy of any little piece of mass is just 1/2, like and u squared, where u is the speed of the little mass element, times dm. So 1/2 m, right, velocity squared. This looks just like the kinetic energy formula that we all know and love. Oh, I forgot to mention that the reason why I mentioned that Wikipedia is awesome is because they have an entire wiki page dedicated to this calculation that we're doing right now. And it's called the page is called effective mass for a spring mass system. So what we want to say is that the mass of the spring is uniformly distributed. So dm is just equal to dy times the density of the spring, which is going to be m per L. Right? So this we have a constant mass per length times a little tiny length will give us the little tiny mass. And this L is just the length that the spring is at any given moment. But that allows us to take this integral over the mass of the system and make it an integral over the length of the system. We can pull out all the constants. then we have to realize something about U. Right? The parts of the spring which are closer to the top of the spring will be going at a slower speed, right? Because the period, right, of oscillation for the whole spring is going to be the same for every part of the spring, right? But but the amplitude for each individual part of the spring is not going to be the same for each part of the spring. So actually, the velocity of each little bit of the spring is going to be proportional to how far down the spring it is. Right, so y over L is the fraction of the length down we are, and then v, right, is the overall velocity of the spring. So this would be the velocity of the mass hanging on the end if we had one. So if you are all the way down the length of the spring, notice that y just equals L, and the velocity of this little bitty mass unit is just the velocity of the tip of the spring. So the velocity of each individual mass unit, at least individual slice of mass, is just a fraction of the speed that the tip of the spring is undergoing. That allows us to change U. We're going to have YV over L squared dy. We need to factor out some more constants here. Again, L is a constant, and the V is also a constant, right? V is just the velocity of the tip of the spring, or the mass on the end of the spring if we had one. So we have m v squared over 2L cubed out front, and then we still need to integrate over the length of the spring. So when we do that integral, we get mv squared over 2L cubed, right, and then y cubed over 3, evaluated at 0 and L. So when we use the top limit, we plug in L for y, we get L cubed. That cancels with the L cubed in the denominator. So we get mv squared over 6. Now, our usual kinetic energy formula is mv squared over 2. So maybe we write this as 1/3 times 1/2 mv squared. And that leads to the definition that for a spring of constant density, that approximately 1/3 of its mass should actually count. So this gives us a quantitative way to describe the error introduced by assuming that our spring has no mass. How does that strike you all? So I like this integral because it's reminiscent of a type of integral that we will be required to do in chapter 11. Sorry, chapter 10.